6th AIC sponsored ATAL-FDP. A very warm welcome to all of you to this prestigious faculty development program on emerging trends in adaptive manufacturing of advanced materials for industrial applications, organized by a Department of Mechanical Engineering of Amritsar Group of Colleges, Amritsar, and sponsored by AICT ATAL. It is indeed an honor for me to stand before this respected gathering of distinguished academicians, researchers, and industry experts, all driven by the quest of knowledge and innovation. This 6-day online FDP scheduled from the February 3rd to 8th February 2025 is a testimony to our commitment to academic excellence and cutting-edge technological advancement in adaptive manufacturing. As per the significance of adaptive manufacturing is concerned, the world is witnessing an industrial revolution where adaptive manufacturing is transforming the manufacturing landscape by enabling customized, cost-effective, and efficient production of complex components. Additive manufacturing allows us to 3D print, complex design, use advanced materials, and adopt eco-friendly practices. These features make it important technology in today's industry. This FDP serves as a platform for faculty members and researchers to explore how additive manufacturing is shaping the future of manufacturing and education. The primary objective of this FDP are to equip educators with cutting-edge knowledge in additive manufacturing technologies, to bridge the gap between practical learning and practical industrial applications, to explore emerging materials and their impact on adaptive manufacturing, the foster innovation and research collaboration among academia and industry, to improve the teaching and learning experience by including adaptive manufacturing concept in curriculum. I am also proud to welcome some of the top experts from well-known universities, institutions, and prominent industries who will be sharing their deep expertise. Each session has been carefully planned to give participants useful insights into different aspects of adaptive manufacturing, including fundamentals and technological advancements in adaptive manufacturing, advanced materials including metals, composites, and nano-enhanced materials, sustainability and hybrid adaptive manufacturing technologies, applications, quality control, and commercialization of adaptive manufacturing parts. As per the highlights of the FDP are concerned, and you all are aware that its date from February 3rd to 8th, 2025, and timing will be for day first. The time will be 6 p.m. to 9:30 p.m. For day 2 to day 5, it will be 6 p.m. to 9 p.m. And for the day 6, the timing will be 2 p.m. to 8 p.m. Our speakers are well-known experts from the industry and top educational institutions, and they will lead session on introduction to adaptive manufacturing technologies, advanced and composite materials in adaptive manufacturing, design for adaptive manufacturing, sustainability in adaptive manufacturing, multi-materials and hybrid adaptive manufacturing technologies, quality control, certification and commercialization, future trends in adaptive manufacturing. The key benefit for the participants for attending the FDP are to gain expertise in adaptive manufacturing for advanced materials, for industrial applications, learn how to integrate adaptive manufacturing into teaching and learning environments to receive an AICT ATAL participation certificate upon successfully completion, and explore the critical role and advanced materials in the evolving field of adaptive manufacturing. To qualify for the AICT participation certificate, participants must attend at least 80% of the sessions, fill up the feedback of the event through your login at ATAL-FDP portal on the last day of FDP, and score a minimum of 70% in the final test. And the test will be conducted on the day of the FDP, last day of the FDP, and its detail will be available on your respective login at ATAL-FDP portal. As we embark on this enriching journey of knowledge and innovation, I urge all participants to actively engage, ask questions, and leverage this opportunity to expand their horizons. This FDP is not just about learning, it is about building a strong community of educators and researchers who can drive transformative changes in the field of adaptive manufacturing. I extend my heartfelt gratitude to AICT ATAL for their unwavering support, to our esteemed resource persons for their invaluable contributions. My Honorable Chairman, Sri Advocate Amit Sharma ji, respected Director Finance, Madam Ragini Sharma ji, our Managing Director, Dr. Jinish Arora ji, worthy Principal, Dr. Kaur Tejpal ji, for their noble guidance, and the organizing team for their never tiring efforts in making this FDP a grand success. Most importantly, I sincerely thank all the participants for their commitment to continuous learning. Let us work together to push the boundaries of knowledge and innovation. I wish you all a highly engaging and fruitful FDP. Thank you and best wishes for an inspiring and enlightening learning experience. I also feel delighted to share that with you that our worthy principal, sir, and Dean Academics and Dean Research and R&D has already joined this ATAL FDP. Now I request to our Dean Academics and my Head of Department, Dr. Upen Kumar Patia ji, to come forward and share his words with the esteemed audience. Over to you, sir.
Dr. Gurpej, am I audible?
Yes, sir. You are audible.
Yes, sir. Very much.
Thank you so much, Dr. Gurpej, for inviting me here. Honorable dignitaries, distinguished guests, and dear participants, a very warm welcome to all of you. It's a privilege to be a part of this faculty development program on emerging trends in additive manufacturing of advanced materials for industrial applications. At the onset, am I audible, sir?
Yes, sir. Yes, sir. Very much audible, sir.
Thank you so much.
Please continue.
So at the onset, I would like to extend my heartfelt thanks to AICTE for giving us chance to conduct this faculty development program. And I would also like to extend my heartfelt appreciation to the organizers for bringing together such an esteemed gathering of academicians, researchers, and industry experts to explore this crucial and evolving field. Speaking briefly about the college, Amritsar Group of Colleges was formerly known as Amritsar College of Engineering and Technology and Amritsar Pharmacy College. Established in 2002 by Amritsar International Education Trust, this premier institute has been duly approved by AICTE as well as the Pharmacy Council of India. AGC, with its magnificent environment and superior learning system, is ranked among the best colleges in the North India. We are affiliated with IK Gujarat Punjab Technical University, Kapurthala, and became the first private autonomous engineering college in Punjab on 19th of June 2014. We were accredited twice by the National Board of Accreditation, that is during 2009 to 12 and 2016 to 18. And in continuous third cycle, we are accredited by the National Assessment and Accreditation Council with grade A in the category of the autonomous colleges. Its tremendous growth in a short spell illustrates its success in the education sector. The institute endeavors to educate the students to become not only competent professionals, but also the excellent human beings who contribute towards the welfare of the society and raise the quality of life of its people. The institute has been established with a noble aim and vision to produce the professionals of highest caliber and values for the industry and society. In today's fast-paced industrial landscape, the additive manufacturing is not just a technology, it's a revolution. It has transformed conventional manufacturing by enabling complex geometries, material efficiency, and rapid prototyping. From aerospace to biomedical applications, adaptive and additive manufacturing is pushing the boundaries of innovation, making production more cost-effective, sustainable, and precise. The 6 days faculty development program is a golden opportunity for all the participants to gain in-depth knowledge of this additive manufacturing technologies and their applications. They also get insight into the advanced materials, including metals, composites, and nano-enhanced structures, and the understanding of the sustainability and hybrid manufacturing techniques. There is also an opportunity to collaborate with the industry experts and like-minded researchers. So I encourage all of you to actively engage, ask questions, and make the most of this platform. This faculty development program is not just about learning, it's about shaping the future of manufacturing education and research. Before I conclude, I extend once again my sincere gratitude to AICTE Training and Learning Academy, that is ATAL, our esteemed institute leadership, and the organizing team for their dedicated efforts in making this FDP possible. I am confident that the knowledge shared over these next few days will be contributing significantly to academic excellence and industrial innovation. And I wish you all a fruitful and insightful learning experience. Thank you all, and over to Dr. Gurbhej again. Thank you, sir.
Thanks, Dr. Bhatia, for awareing us about the institute and about the FDP. I guess participants understand that FDP has a vital part in their life, particularly on the topic of additive manufacturing. As per the schedule is concerned, so Dr. Gurupej, the coordinator of the event, has already told that it is of the 6 days. For today's day 1, we have started with the inaugural, and there will be the 2 sessions. Session 1 will be on the topic of Introduction to Additive Manufacturing Technologies, which will be delivered by Professor C.P. Paul, Professor and Head, Rajaraman Center, Advanced Technology, Department of Atomic Energy, Government of India. His experience is around 20 years. So second session of the day will be delivered at 8 p.m. to 9:30 p.m. on the topic Advanced Materials for Additive Manufacturing, and expert of the event is Professor Neeraj Bala. She is the professor and head at National Institute of Technical Teaching Training Center and Research, Chandigarh. Her experience is around 18 years. Moving further for the schedule to the day 2. So on the day 2, we will learn about the topic additive manufacturing of metal alloy and high performance materials. It will be delivered in between 6 p.m. to 7:30 p.m. and expert will be Madam Manpreet Kaur. She is a professor at Baba Banda Singh Bahadur Engineering College, Fatehgarh Sahib. Her experience is around 17 years. 4th session will be delivered in between 7:30 p.m. to 9 p.m. on the topic Design for Additive Manufacturing. So expert will be Professor C.P. Paul, means first expert who will deliver the session 1, Professor C.P. Paul. He is the professor and head, Raja Raman Center, Advanced Technological Department of Atomic Energy under Government of India. As per the day 3 is concerned, so it will be started at 6 p.m. to and end at 7:30 p.m. Session 5, it is on the topic sustainability in additive manufacturing. It will be delivered by Mr. Piyush GUK. He is a founder and director of New OSA, VNIT, Nagpur, Maharashtra. Session 6 on day 3 will be delivered at 7:30 p.m. to 9 p.m. and on the topic nano-enhanced and functional material in additive manufacturing. It will be delivered by Dr. Himanshu. He is a research associate at the Department of Material Science and Metallurgy, University of Cambridge, and his experience is around 15 years. Session 7, it will be delivered on day 4th of the FDP in between 6 to 7:30 p.m. Topic will be multi-material and hybrid additive manufacturing. The expert of the event will be Dr. Surjit Kumar Chobe. He is the postdoctoral research fellow, Faculty of Engineering and the Built Environment from the Department of Mechanical and Industrial Engineering Technology, University of Johannesburg, South Africa. He has an experience around 12 years. 8th session, which will be second session of the day 4, on the topic composite materials in additive manufacturing. It will be delivered by Dr. Hitesh Vasudev, professor at Lovely Professional University, Jalandhar. He has almost 15 years experience in the relevant field. Day 5, it will be session number 9. So it will be on the topic explore future trends such as multi-material and hybrid additive manufacturing technologies. It will be again delivered by Dr. Hitesh Vasudev. He is professor at Lovely Professional University, Jalandhar. Session 10 means session 2nd of day 5 on the topic case studies of additive manufacturing in industry. It will be delivered by Mr. Gagandeep Singh. He is the assistant manager at Manenda Corporation Limited, Noida. He has experience around 15 years. On the last day, day 6, session 11th will be delivered on the topic future trends in additive manufacturing. The expert of the session will be Mr. Karanjit Singh Pannu. He is a deputy chief engineer at the Ajnala Corporate Sugar Mills, Ajnala. 12th session will be delivered in between 3:30 p.m. to 5 p.m. 3:30 p.m. to 5 p.m. on the topic quality control testing and certification of additive manufacturing parts. It will be delivered by Mr. Chetan Sharma. He is from Tata Consultancy Services, Gurgaon. His experience is more than 10 years. The last session of the FDP on last day, day 6th, will be session 13th, will be delivered between 5 to 6:30 p.m. on the topic intellectual property and commercialization in additive manufacturing. It will be delivered by Mr. Neeraj Kumar. He is the senior design engineer at GNA Gears Limited, Fagwada. He has a relevant experience around 15 years. After that, it is followed by online test and feedback. So dear participants, do remember that test is mandatory for everyone to qualify for the participation certificate. Minimum passing percentage is 70%. So it will be available through your login at the ATAL portal. So you should have to attempt the test through your login. And at the end, at 7:30 p.m. to 8 p.m., there will be valedictory session of the FDP. So this is all about the schedule of the FDP. Now we will have to wait for 4 or 5 minutes. We are in touch with the expert, Professor C.P. Paul. He is busy somewhere. He will join us shortly. In case he's unable to join, we have already requested Mr. Hitesh Vasudev. He is professor at Lovely Professional University. He will deliver the expert talk on his place. And basically, this is a swapping of the lectures between Professor C.P. Paul and Professor Hitesh Vasudev. So, dear participants, kindly bear with us for within 4 or 5 minutes, it will get started. Thank you. Dear participants, all sorry for the inconvenience due to unavailability of the Dr. C.P. Paul. He was the first speaker of the day. So we have requested to Dr. Hitesh. He's a professor at the Lovely Professional University. He will start this day one session. So, Dr. Hitesh, am I audible to you, Dr. Hitesh? Dr. Hitesh, am I audible to you? Am I audible to everyone?
Yes, sir, you are audible.
Okay, thank you, thank you. I guess there is some connectivity error towards the Dr. Hitesh, right? Dr. Hitesh? Yeah, there is a message wait. Thank you, Dr. Hitesh. In between, a request to Suraj, who is assisting us, kindly give the hosting right to Dr. Hitesh so that he can smoothly conduct the session.
Sir,
Suraj,
I already make him the
you have given the right
host.
host right to him. Thank you, Suraj. I again request to Dr. Hitesh. Sir, am I audible to you?
Good evening, everyone. Am I audible?
Good evening, sir.
Yeah.
Yes, sir.
Good evening. Very much audible, Dr. Hitesh. Please.
Hello. 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 Hello, Dr. Atesh. Are you ready? Hello. Hello. Dr. Atesh, are you ready?
Yes, sir. We can proceed, sir.
Okay. Let us start our first session. The expert of first session is Dr. Hitesh Vasudev. Dr. Vasudev is currently working as a professor in the School of Mechanical Engineering at Lovely Professional University, Fagwada. His research area including surface engineering, thermal spraying, HVF flame spray, cold spray, and plasma spray, and microwave cladding. Recently, he has listed in World Top 2% Scientists published by Stanford University and elsewhere in 2023. He has been awarded a top cited paper award in 2022 by IOP Publishing Publishing United Kingdom in review category. He has won Research Excellence Award in 2019, 2020, 2021, and 2023 in Lovely Professional University. He has more than 100 such papers in SEI and Scopus Index journals. He has 10 self-authored books and he published more than 20 book chapters. He has granted patent on title High Temperature Oxidation and Erosion Resistant Alloy 718 Alumina Composite Coating. He has organized a national conference and international conferences. He has received a seed money for project title Fabrication of Coating for Biomedical Applications. Project number LPU DRD Seed SAC 140222 from Lovely Professional University. I once again thank you, Dr. Hitesh Vasudev, and over to you. Hello, Dr. Hitesh, I am audible?
Sir, is my screen visible?
Yeah, very much visible, sir.
So first of all, I would like to thank all the management and coordinators of this ATAL-FDP program who have invited me to deliver a lecture on additive manufacturing. So, especially I am thankful to Dr. Gurpreet Singh, who is a coordinator of this one, and Mr. Rajveer Singh. So I was a student of Rajveer sir during my graduation. So it is my honor to deliver a lecture at your prestigious institution. So let us start with the session. So the first topic which I was given by the coordinators of this ATAL-FDP is the introduction to the additive manufacturing. Am I audible, sir?
Yes, sir, you are audible.
Okay. So presently, I am serving as a professor in mechanical engineering department at Lovely Professional University, and at the same time, I am deputed in the research and development cell of the university as well. So we are taking care of publication part as well for the university and the conduct of conferences and other research related parameters we are also taking care of. So let us come to the introduction of this session, that is the introduction to the digital fabrication or introduction to the additive manufacturing. So instead of additive manufacturing, I would say digital fabrication, because we have to start with the fundamentals of additive manufacturing, but at the same time we have to consider the concept of digital fabrication. So most of us belongs to the domain of mechanical engineering and their verticals. So there are different verticals of mechanical, like material science is one of them, thermal engineering is one of them, production and manufacturing is one of them. So when it comes to mechanical engineering, so there are many associated verticals with mechanical engineering. And in all the verticals, there is a need of digital fabrication, which can be fulfilled by using additive manufacturing. So we have to introduce the concept of additive manufacturing. It is most likely famous with the name of 3D printing in most of the institutions rather than additive manufacturing because of its application. Now, coming to the contents which I have included in this particular presentation, that is the need of digital manufacturing. or you can consider this as a need of additive manufacturing, followed by prototype. What is prototype? Then what are the different types of prototypes? What are the roles of prototypes? Then what is rapid prototyping? It is very common as well as famous term. Then the different phases of RPT, that is rapid prototyping. And finally, fundamentals of rapid prototyping and its advantages, because there are many other processes which can be used for the fabrication of materials other than additive manufacturing. So we have to taken care of those processes as well as at the same time. Now, so what is actually digital fabrication? So in digital fabrication, what we actually do, we use computer to assist the manufacturing part. So whenever we have to design a product, then in the designing of that product, we have to use computer. How computer can assist us and how we have to use computer in manufacturing. So when we are using computer in manufacturing, then it is called digital fabrication. So there are many forms which we will discuss later on, and in this case of digital fabrication, the most often term that we use is CAD, computer aided design, because once we discuss manufacturing part, along with that we have to consider the aid of computer along with the manufacturing part. So first of all, we use CAD in case of digital fabrication. And even if you talk about additive manufacturing, we use computer aided design in the beginning. And then that CAD is transferred to the CAM, which is called computer aided manufacturing. So these are the very common terms which we use when we study various courses related to the manufacturing during our graduation courses, right? So what is the purpose of CAD? Whenever you are going to design a product, then obviously you need its drawing. So drawing is the primary requirement. So here we can consider an example. So being a teacher, I use a marker in the class, then duster in a class. So let us say I have to manufacture a marker. So in marker, there are three parts. First is the cap of the marker. Second is the main body of the marker. And third is the tip of the marker. So when we assemble these three, we'll get a product that is called marker. Similarly, if I consider an example of a duster, and there are two parts in a duster. One is the form which is stick to the polymer. Polymer is the main body of the duster. So there are two parts associated. When we assemble it, it is called duster. Now coming to the manufacturing part, whenever I have to design the main body of a duster, so what I have to do in the beginning, I have to prepare its drawing. Now for drawing part, what we use CAD. Here it is, computer aided design, where we are using computer for the purpose of designing. So I have to prepare its drawing, and obviously instead of using drawing sheets, I have to use some dedicated software package, like AutoCAD is one of them, right? And other than AutoCAD, there are many other software packages that can be used, like SolidWorks, then ProE Professional Engineer is there, then STAAD Pro is there, which is used in civil engineering. Similarly, there are many more. So I have to prepare its drawing in the CAD. Then for its manufacturing purpose, I have to transfer that drawing to the CAM, which is called computer aided manufacturing. Here it is. Because in the beginning years of additive manufacturing, it was basically used for the manufacturing of polymers. So that is why here I am considering two examples. First one is the duster and second one is the marker, because it is made up of a polymer that we call which is one of the classes of a material, polymers, and usually we call it plastics. So it comes under the class of plastics. So once we are ready with the drawing, then we have to transfer that drawing to the CAM, which is called computer aided manufacturing. So there may be some computer or program or software which is linked with the machine tool. Machine tool means that machine which is used for the manufacturing of that particular product. So that part is CAM. So this is how CAD and CAM is integrated for the fabrication of different products. Then coming to the next part, the output of the CAM. So I'm reading out the third point. The output of the CAM software is the data that directs a specific additive and subtractive manufacturing tool such as 3D printer or CNC milling machine. So why I'm quoting these two manufacturing processes, that is additive manufacturing and subtractive manufacturing. So can someone shed light on this? What is additive? What is the meaning of additive and what is subtractive? Anyone from the audience?
Yeah, this is Dr. Gaurav Hitesh, sir.
Yes, sir.
Additive means when you add the material layer by layer on a to make the final part. And in subtractive manufacturing, basically we have a drawing and we have given the block and we are doing certain machining operations on that. And then we are removing the material and then we will make the final part of that block. That in subtractive, we will remove the material.
Exactly, Dr. Gaurav. So basically, in additive manufacturing, we have to add a material for the manufacturing purpose. And in case of subtractive manufacturing, we have to remove the material by means of some machining. For example, cutting of a material. So here I can consider a simple example of a lathe machine where single point cutting tool is used and we have to cut the material. We have to remove the material to get a final product. So grinding is another application where we remove a material. That is also an example of subtractive manufacturing. But on the other side, if we talk about additive manufacturing, we have to add a material. So we are basically adding a material to having a final product. So 3D printer, or we can say 3D printing. 3D printing is one of the examples of additive manufacturing process, whereas machining. So here I have quoted CNC milling machine. So this is one of the examples of subtractive manufacturing where we are removing the material to get a final product. So this is where we can use CAM software to assist manufacturing. Right? So it is applicable in both, in conventional manufacturing processes as well as non-conventional manufacturing processes. Now I want to know from the audience, if I have to define a 3D printing process, so in which category we can consider this process? So conventional machining process, or manufacturing process, or non-conventional manufacturing process? Yes. So if you want to add something into it, you are welcome.
It's non-conventional.
So okay, it's non-conventional. And how we define conventional manufacturing processes and non-conventional manufacturing processes? So on what basis we define this
When we
category?
disturb the material during cutting operation for final product, that is called conventional machining. And when we do not disturb the material and just add the layers and minimum dislocation, we can say, so that is called non-conventional.
Okay, so here you are mentioning the disturbance or dislocation of the material. So here we have two things. First is the additive manufacturing process, that is 3D printing, and second is subtractive manufacturing process, that is CNC machine tool. So basically in 3D printing, why we consider this one in a non-conventional manufacturing process? Because here we are assisting the process with various software packages and computer. So here we are moving towards the automation, or you can say automation. So it comes under the category of non-conventional manufacturing systems, right? So here in this presentation, I have incorporated some case studies as well. So the link is provided. I'll be sharing this presentation with the coordinators and they will be sharing with you. Okay. Now coming to the application of 3D printing and how it is useful in various sectors like in computer science. So why I have mentioned computer science? Because now we are into the era of generation Z, Gen Z, Gen Alpha. So where most of us are familiar with the digital platforms, and most of us are incorporating the application of various tools which are linked with computer science engineering. So here I would mention the various applications of AI and ML. So we are integrated our subjects, our courses, our programs with AI and ML. So we have to also incorporate computer science with the same, because however we were using this one in the initial stages as well, but now it is very familiar and famous. So that is why I have incorporated this word computer science. So computer science and 3D printing. So here I have mentioned uh, one case study, how this is useful, how 3D printing is useful, how additive manufacturing is useful. So it is otherwise, if we talk about the other processes which were used in the initial stages before the application of additive manufacturing, in those processes there was the main uh, reason why we have adopted the additive manufacturing is to avoid the wastage of material. So in order to avoid the wastage of a material, and there are other parameters at the same time which I'll be sharing later on, we have now started using this application in many typical engineering applications. So one of them is here is the use of 3D printing in biomedical implants. So before the use of additive manufacturing in biomedical implants, there was a use of different materials like titanium and its alloy, magnesium and its alloy. Then HAB is one of the famous material, HAB, and some composites which are which is a composite which is a combination of these parent material and some other materials which we call, which we consider as composites, and many more materials. But the processes at that time which were used for the manufacturing of biomedical implants were, in most of the cases, it was machining. So in machining, if you have to machine a hard material, you know, a dedicated tools are required which are capable of machining a hard materials. And at the same time, if the material is costly, so as I mentioned, titanium and its alloys, magnesium and its alloys, so these are very costly materials. So as compared to the materials which we are using in typical engineering applications like steel and its alloys, right? So these are very dedicated and costly materials. So in that case, we have to avoid the wastage of the material while cutting of the materials. So biomedical implant is one of the application where we have used additive manufacturing and still we are using it. And now there are many processes that have come even after 3D printing. Or you can say these are the extended forms of 3D printing. So in this particular case study, so here you can see the first human to receive a 3D printed implant. So that was a cancer patient. So that was a custom designed rib cage to replace his sternum and pieces of ribs severely damaged when doctors remove a large tumor. So there was a problem of cancer, and which implant was used in this particular case study? That was a rib cage manufactured using 3D printing. Right now, the thing is the difference. What is the difference when we are talking about uh, the products which are manufactured using conventional processes and the products which are manufactured using 3D printing or additive manufacturing? So what are the requirements and what is the difference? Yes, any idea? So why we have introduced the concept of additive manufacturing instead of already existing manufacturing processes? Any idea? Any point if you want to quote?
Yes, sir. Less material wastage.
Yeah, this is one of the parameters which I have already mentioned. Other than this, any other point?
Complicated geometries.
Yes. So that is the most important parameter. So in case of additive manufacturing, any complex shape can be manufactured. Because in case of machine tools are restricted up to some degree of freedoms. So if you want a curved surface, let us say you want to fabricate a spherical ball. So it is very difficult to fabricate a spherical ball using machine tools. So if I quote the same machine, that is CNC milling machine. So the number of degree of freedom which are required are more, and it is very difficult to manufacture a complex shape like a sphere, because in our human body the shapes are like this, spherical shapes. If we talk about joints, the shape is spherical, right? So in most of the joints the shape is spherical, right? So similarly, there are two parameters which are important. First is to avoid the wastage of the material. Second is, here we have to take care of the complexity of the design. So complex shapes can be easily additive manufactured. So these two are the most important parameters. So that is why when there was a requirement of a rib cage, so the geometry of a rib cage is very complex. Even if you think about, if you imagine, if I have to manufacture a rib cage which is made up of some metal, let us say metal or any alloy, so it is very difficult to, which machine I have to use, how much degree of freedom that machine should have, right? So similarly, when I come to 3D printing, it automatically comes to my mind, I can easily fabricate any complex shape. So you might have seen dummies of some implants, dummies of some smartphones, then dummies of some machine tools, even a dummy of a bullet and scooter or a car or a plane. Because when I was taking a training of 3D printing during my graduation course, then we were shown a very small models of uh, some products, like the products which are actually manufactured in some industry. So those were shown to us as a 3D printed parts. But in actual application, it is also used, like in this particular case study. So they have used this concept in rib cage, because now we are not restricted to the use of only polymers. Now we are capable of manufacturing composites as well, and even metals. So we can fabricate metals as well. For example, for the fabrication of the products which are made up of metals or alloys, those are manufactured by using a metallic printers. So if I am not wrong, it is available at IIT Ropar with Professor Mahajan, because I have gone through their website few months back. So they have mentioned this facility in their central instrumentation facility, which they offer to everyone. So you can access that facility. So over there, metallic printer is also available. Otherwise, if you talk about a 3D printer, which is capable of producing a parts using polymer and even composites, if you want to manufacture, so we also have 5 3D printers at our university. So we have design and innovation studio. You can also access that facility. It is available online as well. And apart from that, in School of Mechanical Engineering, we have a dedicated 3D printing lab where we have 3D printers. So you can use those 3D printers also. So as of now, we don't have metallic 3D printer. So hopefully in the coming years, we'll approach to that facility also. So this is one of the application. Now, how 3D printing works. So when I'm quoting 3D printing, it means it is one of the applications, major applications which we are familiar with. So how 3D printing works. So these are some of the steps how it works. So first of all, obviously you have to prepare a drawing of your product using a software packages like AutoCAD, right? So first of all, there is an application of CAD. Then after that, you have to convert that CAD model, which is converted into an appropriate format, that is such as STL. So this is not restricted only up to STL. So why I'm mentioning STL? Because this is one of the manufacturing technique, or you can see the fundamental principle working behind the 3D printing. So you have to convert, because in AutoCAD we have a format in DWG, that is drawing. So here I am highlighting. So like if I have a format of PDF file, it is like PDF. So in case of Microsoft Word, so it is somewhere it is text, somewhere it is some other format. So in case of AutoCAD, we have this format, that is .dwg, means drawing. So we have to convert this format into STL. And how it is converted? So let us say we have a 3D printer. So the computer, which is the computer system, which is linked with the 3D printer, in that 3D printer, we have a facility of converting this file into STL format. So here we are basically converting .dwg format into STL format. So the explanation is given in the coming slides. Then, so here the STL file is transferred to the computer that directly controls the 3D printer. So I already mentioned this thing, the computer which is controlling or linked with the 3D printing. So we are basically giving this file as an input to that computer, that is .dwg. Then the further step is it is ready for job. The fourth step, it is ready for job. So in 3D printing, in the 3D printers, so there are containers which are loaded with the appropriate printing materials. So those printing materials are like polymers and binders. So there are other forms of materials as well as, so the materials which we can use in a 3D printer can be in the form of powder, wire, or liquid. So there are 3 states of materials which can be used in different applications of a 3D printing. So however, here I am mentioning the class of a material, not its state, right? So polymer and binders, and a foundation tray for finished object to be set up. Then obviously the printer builds the object layer by layer. Layer by layer. So here I want to quote 2 examples. First example is 2D printing, and second example is 3D printing. Can someone differentiate between 2D printing and 3D printing? What is 2D printing and what is 3D printing? Yes, any idea?
I think 2D means X and Y direction, and 3D X, Y, and Z.
Yes. So when we are dealing with the two coordinates, two axes, then that is obviously a 2D. When we are dealing with the three axes, that is a 3D. So the perfect example of a 2D printing is the printing of a paper from a printer. Because we consider 2D as that entity where we have zero or negligible dimension in the third coordinate, or we can say third axis. So the thickness of the paper is negligible. So we can consider that one as a 2D printing. Like similarly, in case of 3D printing, when we are dealing with some thickness, when the third dimension is added to an object, it comes under the category of 3D. So basically what we are doing, we are defining 3D. So how 3D, three-dimensional object or three-dimensional entity is defined, where three dimensions are required to define an object. Three dimensions are required to define the geometry of an object. So when we are adding number of layers, so here I am mentioning stack of a paper, like a paper rim. So that is a stack of paper, stack of 500 pages. So because that has some thickness. So here the same concept is applicable in case of 3D printing. So when we have one layer with negligible thickness, we can consider that one as a 2D. But when we keep on adding n number of layers to achieve some thickness of the material, that is a 3D printing. So that is why the printer builds the object layer by layer. Now, the last step in the 3D printing is, when the 3D printer has completed the building process, the object is obviously we have to remove the object from the 3D printer. Then it may require some post manufacturing actions such as brushing, polishing, and maybe some other processes. So if you are from additive manufacturing background, then you can give some inputs to this point. About the post manufacturing actions. Yes, anyone from the audience, if you want to add something into the post manufacturing actions in a 3D printing or in a additive manufacturing.
Heat treatment, sir,
Yes, in
to
case
improve
of
the properties.
yes, in case of conventional materials like steel and alloys, so what we do, after the processing of the material by using different techniques, we have to perform certain heat treatments. So those heat treatments can be seen in forgings, in other manufacturing units. So the nearby units, because I belong to Hoshiarpur city, so here we have a GNA Axles, then International Tractor Limited, Sonalika Tractors. So they are a manufacturer of automobile parts, basically. So in automobile parts, steel and its alloys are used. So in most of the cases, steels are used. So when we process the steel at high temperature to get some shape, then we need certain heat treatment processes after the manufacturing process, after the completion of the manufacturing processes. When we are dealing with the high temperature, so there are some stresses that may set up in the material, which we call residual stresses. Right. So for that purpose, we have to perform recrystallization. So recrystallization is one of the important parameter which we use in case of steels. Similarly, in case of 3D printing, when you have done with the processing of a material, so you may go for some post-processing techniques, which can enhance the properties of the material. Okay. So here I want to quote one example for the 3D printers. So in case of 3D printer, when we have to maintain the aspect ratio of the product. So here I am mentioning the aspect ratio of the product. So let us say, so is this a red geometry visible on the screen?
Yes,
Am I
sir.
audible?
Yes, sir. Visible.
Visible,
Yeah.
sir.
So let us say I have to manufacturing this geometry. Now in this geometry, there are two dimensions. First is in the x-axis, second is in the y-axis. So in x-axis, you can see the width is very less as compared to the height. So here I am considering two dimensions. First is the width of this geometry, second is the height. So here the aspect ratio of this geometry is somewhat odd. It seems somewhat odd. Like if I have to maintain the aspect ratio of this geometry, so I have to increase the width of this geometry. Like this. Now here you can see it seems like a square. So here the aspect ratio is, so what is the aspect ratio here? Yes, any idea?
1:1.
Yes. So we can call it 1:1 at this moment, right? We can call it 1:1. But if I keep on increasing the height and decreasing the width of the geometry, so in the 3D printing or in the 3D printer, it is very difficult to fabricate this geometry. Why? Because the height is very much extended as compared to the width. So in this case, some support is required. So you might have seen a support material in 3D printer. So there are two materials which are used in a 3D printer. One is the material which is used for the fabrication of the product. Second one is the support material. So in this case, we have to provide support to this geometry. So here we have to provide a support. Let us say one support is added here on this side. Similarly, we can insert one support on the other side. Like this. Now these two supports are supporting this geometry. And it is easy to fabricate this particular geometry due to its odd aspect ratio. So when we are fabricating a product in a 3D printer, after the completion of the fabrication process, we have to remove this support material because this is not a part of an object. So that comes under post manufacturing actions. So if the support materials stick somewhere on the surface of the geometry, then we have to, what we have to do? Here it is mentioned. We have to use this one, that is brushing. If the surface has damaged, let us say you are removing a support material and the surface gets damaged due to the removal of a support material, in that case you have to go by this post manufacturing action which is called polishing. So these are few commonly used post-manufacturing actions in 3D printing. So this is the, here you can get an overall idea about the digital fabrication process. Like, first of all, we have to give input in the form of spreadsheet, which is related with the computer engineering part. Otherwise, we are using computer, we are using different software packages like AutoCAD, SolidWorks, StatPro, and others to prepare our drawing, which is to prepare our drawing of the object which is to be manufactured, right? So that is the first part which I have elaborated here. Here the first part. So computer aided design. Then we have to prepare a G code for the manufacturing purpose. Obviously, if you want to fabricate some material, if you want to prepare some object, then obviously uh, you have to provide the dimensions of that geometry. Let us say in this case, if I have to manufacture this geometry, first of all, a nozzle is there in the 3D printer. That nozzle will move in the x-axis uh, by some dimensions which are given. Let us say its width is 50 mm. Then the nozzle will move in the x-axis by 50 mm. Then it will go in the upward direction by the thickness which you have given for the one stroke. That is, here we can consider 1 mm. So it will go upside by the 1 mm and then it will go back to the initial position here in minus x direction. So in this way, two layers will be formed, right? And how it is decided in which direction the tool is going to move initially, and what will be the first step, second step, third step, and so on. So this is decided in the G code. Here you have to define the movement of the nozzle. In case of machines, movement of the tool. So here we have to define the movement of the nozzle so that it can manufacture a product layer by layer. Then third is the production. Obviously, in the production, we have to define as atoms. So what we are why we are considering atoms here? Atoms here, maybe you can treat these atoms as a group of batches. So you might have gone through the term batch production, mass production in the manufacturing. So the same concept is applicable here. So you have to craft the physical object using additive or subtractive techniques. But here we are very much interested in additive manufacturing. So I am talking about 3D printing only, right? Otherwise, this computer aided design and G code generation is also used in subtractive manufacturing processes like in CNC milling machine. So over there, obviously, first of all, we have to prepare a model in the CAD software. Then we have to move that particular model into the CAM. Then we have to prepare a G code. Then the tool will run to remove the material and to get a final shape of an object. But here in this case, the process is same. But at this stage, at the production stage, here there is no removal of the material. Yes, there is a removal of the material, but that falls under the category of post manufacturing actions like brushing, polishing, and other post manufacturing actions. So here I'm going to play one video. So, what is the main purpose of showing this video? The main purpose of showing this video is we can use this concept in additive manufacturing process as well as in subtractive manufacturing process. So if you want to use this concept with the polymers, then obviously we have to change the technique. Instead of addition of a material, we can introduce a laser. So laser is used to cut the material. So here we can use laser for the cutting purpose. So both can be done with the help of uh, digital manufacturing. So why I'm more likely focusing on digital manufacturing? Because it is directly linked with the additive manufacturing. Or you can say one of the application, additive manufacturing is one of the application of a digital manufacturing. And 3D printing is one of the applications of additive manufacturing, which is uh, mostly used in most of the cases, like in our institutions, our nearby institutions, where the graduate students are preparing models using 3D printer. So that is why we are more likely focused on this. Now, what is the need? Keep it in-house. So we can use this one as in-house facility. So you can use a 3D printer at your house also. So there is no special setup which is required. Like in case of conventional machines, first of all, you have to prepare a foundation. Then you have to go with the commissioning of the machines. Like if I quote the example of a machine shop in our institution. So I was also a part of establishment of a machine shop at my institution. So where uh, we have to use the concept of foundation and commissioning of machine tools, right? So that is a difficult part. So it is very difficult to install a machinery. But in case of a 3D printer, we can use this one like a oven, as we are using microwave and oven in at our house. So in the same way, we can use 3D printer. So it is completely a green technology, a sustainable manufacturing process, which is the need also, today's need. So we know the importance of sustainable development goals. So there are 17 sustainable development goals, out of which we are using many, but we are not aware of it. Like there is SDG 11, which is related to the industry. So there are many more others. So this is completely a green technology, sustainable manufacturing process. So the first need is we can use this one as an in-house facility. Then easy to test. So various functions can be performed, various steps can be reduced for the manufacturing by using a 3D printing. Let us say you want to design a product, and uh, before the designing of the product, you have to prepare its drawing. So let us say you are done with the first part, that is the preparation of a drawing by using CAD. Now you want to finalize that product, and to finalize that product, you have to show that product to your seniors, to your colleagues, who are the, you can say, the final authority who is going to sanction your product design. So you have to convince your team. In an industry, you have to convince your team that, sir or ma'am, this is the final product, and uh, these are the features of this product. So I have prepared this product to you. If some important change
Dr. Hitesh, you are not audible.
Network issue. Network issue.
Dear participants, sorry for inconvenience. There is some connectivity issue towards the expert end. Kindly bear with us. Thank you.
Audible, sir?
Dr. Hitesh, very much audible. Kindly continue, please. Thank
Yes.
you.
So when we are done with the 3D modeling of our product, then we have to finalize it. And once we have finalized our product, then we can fabricate that 3D model into an actual product by using a 3D printer. Now, in case of polymers, if you want to perform some testing on that uh, prototype, then you can do. For example, you want to test your material uh, for a scratch test. So you can perform test on that 3D printer, 3D printed prototype. If you want to perform some test which is related to the temperature conditions, you can go with the prototype. However, that is not a final product, but still you can test it. And here we are considering that particular product as a prototype of the final product. Then by doing so, we can save money. Otherwise, what we have to do, we have to fabricate that product by using our actual machine tools again and again. But while doing the prototyping using the 3D printer, it is convenient and easy way to save money as well as time, as well as to save your machine tool, right? Then spot early errors. So if you have prototype in your hand, you can make many changes. You can alter your design. So there are many possibilities which are linked with the 3D printing. That is why digital manufacturing is very much required at the early stage of the product designing. Now coming to the prototype. So because I have mentioned this one in the previous slide uh, about the prototype. So here it is the replica of something. Prototype is the replica of something. And why it is important to have a prototype in the beginning. So I have a very small clip on this.
Prototyping is a crucial part of the product development process, but traditionally it has been a bottleneck due to the high costs and long lead times. Producing prototypes that look and work like the final product historically requires the same traditional manufacturing processes used to create the final part, but these methods require costly tooling and lengthy setup. With rapid prototyping tools such as Formlabs 3D printers, anyone can turn ideas into realistic proofs of concept and advance these concepts to high-fidelity prototypes that actually look and work like final products. Best of all, 3D printed prototypes are cost-effective, enabling teams to create dozens of affordable prototypes with a quick turnaround. In this video, we'll walk you through the fundamentals of rapid prototyping, its applications, and how 3D printing can help you develop prototypes quickly and cost-effectively. What is rapid prototyping? Rapid prototyping is the group of techniques used to quickly fabricate a physical part from a three-dimensional design. With rapid prototyping, engineers and designers can create a better final product, iterating several times between digital designs and physical prototypes with a quick and cost-effective workflow. Here's an example of a rapid prototyping workflow with 3D printing. A typical model takes a 24-hour design cycle. First, design your project in CAD during work hours. Next.
So this is the first stage of the product design. That is the use of a CAD model to have your final product in the form of 3D model. That is the first part, or you can say first step.
3D print the prototype parts overnight. In the morning, clean, measure, test, create assemblies, and collect feedback on your design. Then, tweak your design and repeat the process.
So here, they are using 3 words: clean, measure, and design. So the first part is cleaning. That is related to the post manufacturing system. So once you are done with the 3D printing of a product, then you have to clean your product. Then you have to measure. You have to measure it. Somewhere if brushing, polishing is required, you have to do that. Then the final part is testing. If you want to test that material, you can do. Because right now, the printers which are capable of printing polymers, so I would rather say every form of material is capable of printing every form of material. So you can test that material. If you're capable of manufacturing a metallic product, then obviously you can perform testing on it. As I am working on the coatings, development of the coatings. So basically, my coating materials come under the class of metals and alloys. So if I am fabricating some material using a coating technique, obviously I can test that coating technique. So similarly, if you are able to manufacture any product in a metallic printer, you can directly test that because you are using the actual material, which is to be used in that final product. So that is why first part is cleaning. If some sport material is stick to the surface, you have to clean it. For final dimensions, you have to measure it. Then finally, you have to test that particular product.
Rapid prototyping applications. Rapid prototyping applications include proof of concept models to help product designers validate ideas, looks like prototypes to evaluate the design, works like prototypes.
So these are some associated things. So I think we should restrict up to the introductory part only. So here is a prototype. So obviously it is a replica of something, prototype. But as the actual materials which are to be used in the manufacturing are very costly. So here I want to quote an example of biomedical implant. So which I mentioned in the very beginning of this presentation. So if I have to manufacture a biomedical implant, obviously the very costly materials like titanium and its alloys, magnesium and its alloys, these are used, right? So before finalizing the product, we can prepare its prototype. And in the prototype, obviously we can use cheap materials. However, the final testing is not possible in that case. Final testing is possible in that case where we are using that material which is capable of manufacturing biomedical implant. Still we can do it. And how it is useful? Because in other conventional or non-conventional machining process, there is a wastage of material. So still we are on the benefit side. Even if we are using the actual material in the 3D printing or in the additive manufacturing, still we are on the positive side because there is no wastage of material. But in case of machining, there is a wastage of material. So here we can prepare a prototype in the beginning and then we can test that prototyping before the manufacturing of our final batch, final production batch. Either it is in the form of batch production or in the form of mass production. So prototype is very important. Now, here you can see in rapid prototyping, what we can do, we can quickly fabricate a scale model of a physical part or assembly using three-dimensional computer-aided design data. So that has already been uh, discussed in the previous slides. So ultimate goal is to deliver a final product. Now coming to the phases of prototyping. So I'm somewhat quickly compiling this. So here the first phase is manual prototyping. So when we have some function in our institute or our at our university or our college, so in that case what we use thermocol to prepare some models. So that is called manual prototyping. We can use sand. So sand is also sand or clay, you can say, a sticky clay, which is used by kids. So we can use uh, thermocol, we can use wool, we can use clay. So that comes under manual prototyping. When we basically use craft based materials, which can be crafted with even with hands, that is called manual prototyping. So we can have uh, many such models which are presented during the cultural events at our institutions. Second phase of the prototyping is soft or virtual prototyping. Obviously, when we are talking about soft or virtual, it means now we are not somewhat, we are completing moving towards the digitalization. So here we are going to use CAD and CAM. CAD for 3D model, for the finalization of a 3D model, and CAM for the manufacturing of that product. So when we are introducing CAD and CAM and even finite element analysis, then it means we are talking about the second phase of the rapid prototyping, which is soft or virtual prototyping. So most of you are familiar with this word, that is finite element analysis, which is usually performed in many dedicated software packages like ANSYS. ANSYS is famous software package which is used for the finite element analysis, and you might have used this one during your graduation or post graduation or during your uh, final PhD degree program, right? So, and the final phase of the rapid prototyping is rapid prototyping itself. So this is the current phase. So we are into the third phase of rapid prototyping. Like we are into the Zen Alpha. So the students whom we are teaching, they are from generation Z. So we are from the current scenario is related to the third phase, that is rapid prototyping. Now we are fully using this technique for every class of material, for metals, for polymers, for non-metals, for composites, for glasses. So any material can be fabricated by using additive manufacturing process. So dedicated 3D printers are required for the same application. So I quoted one example. Maybe it is available at PAC also, Chandigarh, or other institutions, but I'm sure it is available. Metallic 3D printer is available at IIT Ropar. So we are right now in the phase 3. That is rapid prototyping itself, where we are using the next level of CAD and CAM, where we are avoiding the wastage of material by using this concept of layer by layer fabrication technique, that is additive manufacturing. Now, what is the difference between geometric modeling and prototyping? So here you can see a difference. So this is a timeline, we can say. So in this timeline, you will come to know about the 3 phases, but I am not going to elaborate it much. So here in the first part, when we had 2D wireframe, so that was the first phase, right? The second phase, when we had introduced 3D curve and surface modeling. So that was the second phase, which is soft or virtual prototyping. And in the first phase, obviously skilled crafts are required. In the second case, what is the requirement? Obviously, software packages are the only requirement. And third one is the rapid prototyping. Now we have every feature of CAD and CAM. In addition to that, we have a machine tool. That machine tool, which we call as a 3D printer. So to assist our CAD and CAM, we have a dedicated machine tool, which is a 3D printer, which avoids the wastage of the material and is capable of producing complex shapes. So these are the two keywords only, which I am mentioning again and again. Avoiding the wastage of a material. Second is the fabrication of the complex geometries. Then fundamentals of rapid prototyping, which are to be used in the additive manufacturing process. So obviously here in this particular, here in the first one here I have mentioned rapid prototyping. So in rapid prototyping, what is requirement? Input is required. So what is required in the input? 3D model, right? And as the format of the drawing is .dwg, as I mentioned in the very beginning, now the requirement of the 3D printer is STL. Sometimes it is IGES. So these are the standard formats which are widely used globally, STL and IGES. So obviously we have to convert that one into STL or IGES. Then after input, so this is input which is required in terms of second phase, that is soft or virtual prototyping. So but once we talk about the material, so the materials which can be fabricated by using 3D printing, so those are available in the form of wire, either wire or powder, or in the form of liquid. So those materials are available in the three forms, and for the same, three different fundamental principles are working behind the 3D printers. So that I will discuss later on. So I have one more session also in this one, in this particular FDP. I will share that one into that session. So otherwise, in the fundamentals, these are the only basics where CAD is required, CAM is required. If you want to perform some testing, that is necessary. Post manufacturing processes, that are necessary. Then the conversion of the formats, that is the necessity. Then output is, we have to avoid the wastage of the material. Then complex shapes can be manufactured. So those things are coming again and again. But in case of input, other than material, so applications, 3D printer is widely used in most of the applications, whether it is aerospace engineering, mechanical engineering. If you want to manufacture a integrated circuit, it is possible. So I showed you one video where the integrated circuit was fabricated using a 3D printer. So in electronics and communication, you can use it. In fiber and communication, optical fibers and communication, you can use it. In aerospace engineering, you can use it, where lightweight materials are required. In automobiles, you can use 3D printed parts, because the parts which are made up of a polymer, which plastics basically, so those can be easily 3D printed. For example, case of a pen, cap of a pen, marker, then case of a duster. Then there are many more other products which are made up of polymers. So in methods, there are various methods that can be used. So those methods are like stereolithography is one of them, which is the fundamental principle working behind the same. Then coming to this one, advantages of rapid prototyping. So this is very important and is the last slide of my presentation. So here you can see relative prototype complexity. So there are two things which are considered in this particular diagram. First one is the timeline starting from 1970 to till date. So here I am considering the last one, that is 1995. Otherwise, you can consider this one as a till date. So the parameter which we are considering against the timeline is the relative prototype complexity. Means the complexity of the product, or you in simple words you can say design of the product. So when we were conventionally fabricating the products using the first phase of rapid prototyping, that was manual prototyping. So that was the first phase. So in that phase, what was the main problem here? Relative prototype complexity. So we were unable to produce complex shapes. Obviously, now we have a concept of accuracy and precision. So that is linked with the measurement part otherwise. But when it comes to the fitment of the two parts in an assembly, obviously we have to take care of many factors like surface finish. Surface finish is one of the factors in that case. So complexity, we can correlate this parameter with the complexity. So it is convenient. It is the most convenient way to understand this first phase. When we don't have a good surface finish, then how we can manufacture a complex shape if we don't even have a surface finish? So the products where you are using wood, where you are using clay, where you are using thermocol as a material, then you cannot get a surface finish. So that was the main problem, right? So, and the second parameter was relative project completion time. So against this parameter of complexity, the time is one of the important parameters, because when we consider the need of 3D printing, additive manufacturing, or digital manufacturing, we have to save our time. So this is one of the major. So here I have mentioned only 5. So we have to correlate these 5 with these topics only. So time is one of the important factors. So it was a time-taking process and complex. We were not able to produce complex geometries. When we came to the second phase, which was the second phase. So here is the second phase, soft or virtual prototyping. So when we went to the second phase, so we introduced the concept of 3D CAD, CNC machines. But still, in that case, we were using subtractive manufacturing processes. So we had to use the machines with high degree of freedoms. So one example here I want to quote, which I have learned during my graduation program. That is the manufacturing of weapons. So we have to take permission from the government for the manufacturing of weapons. Even we are not allowed to do the same. So if you have to manufacturing a weapon, obviously you need dedicated machine tools with high degree of freedoms. So in that era, that was possible. But the process that was used was subtractive manufacturing process. And still we were not able to produce complex geometries due to this disadvantage. That is the availability of the machine tools with high degree of freedom. So why I am mentioning high degree of freedom? High degree of freedom means the tool is capable to move in n number of directions, is capable to uh, follow a trajectory for performing a curved machining on a curved path, right? So these were the some examples in the second phase. Now coming to the last phase. Here in the last phase, we have a concept of additive manufacturing. So what is SLA? It is a stereolithography. What is SLS and FDM and LOM? Do you want to mention something on this? What is SLS, FDM, LOM? Anyone?
I think SL is selective.
Yes, SL is selective laser sintering. FDM is fused deposition modeling. LOM is laminated object modeling, and so on. So these are the fundamental principles which are working behind the 3D printer when we have to use material in the form of powder, either powder or metal or liquid. So these are the fundamental principles which are working behind the same. So this is the introduction to the additive manufacturing. So this is only from my side for the session. Thanks. If you have any query, you can ask.
Thank you, Dr. Atesh. It was great session, and I hope all participants gained a lot of knowledge about this topic. Participants, any query from your side? Hello? Any question? Am I audible? Hello?
So these were the some introductory parts of additive manufacturing. So Dr. Gurpej, I'm very thankful to you for giving me an opportunity to deliver a talk on the introduction to the additive manufacturing. So rather this one, rather additive manufacturing, we can correlate this one with the digital fabrication as well. Because now we are introducing many terms like AI, ML, and many more with our core branches like mechanical and the different verticals of mechanical engineering. So we have to correlate this concept with our concepts as well, because we are already using a computer in the same.
Thank you, Dr. Atesh. Am I audible?
Yes, sir, you are audible.
Thank you, sir. It's a very good session. Any question from your side?
Your session was wonderful,
Okay.
Dr. Hitesh. This is Dr. Gaurav.
Thank you so much, sir.
Yes, I have one question.
Yes, sir, you can.
Like Modi government is talking about this Viksit Bharat in 2047. So what role did additive manufacturing plays in that to achieve that goal, Viksit Bharat?
Sir, government has already provided some core areas of uh, projects. So there are 8, I think. So because here at LPU, we have a dedicated department of sponsored research. So we are dealing with that part also. And recently, ISRO has also introduced one ISRO basket where we can submit our projects. So in that basket, I'll be sharing the link also with you in the group. In that basket, uh, you will have exposure over the use of additive manufacturing in different components in space applications. Because some parts which we have to use in that particular application is for one time use only. Some parts are reusable parts. So they are majorly concerned about the reusable parts for the space applications. So what we can do, we can introduce the concept of additive manufacturing for the fabrication of those reusable parts. Because I am from coating domain. So if I fabricate any material in the form of coatings, then obviously I have to coat a layer over a material, over a metallic material. But in case of additive manufacturing, you can have a prototype in the beginning. That is the main advantage of the additive manufacturing technique. So you can have a prototype in the beginning, and at the same time you can test the prototype. So this is how we can contribute in a one way. Second way is, you are talking about Viksit Bharat. So in our university, we have received 4 projects on Viksit Bharat 2047. So those are very much related to the sustainable development goals that are SDGs. So the main advantage is, in Viksit Bharat, we can have a collaboration with the other branches. So we can have transdisciplinary research instead of disciplinary research. So like we can collaborate. Here we have a dedicated 3D printing lab, and we have a research group also where 5 people from different domains are working, like one from mechanical, another from electronics. So they can share their views about their problems and can work at a same platform, because additive manufacturing can be used for every application. So that is my suggestion about Viksit Bharat. So overall goal is to have green technology. That is the fundamental goal of Viksit Bharat 2047. So what we can do, we can have a transdisciplinary research for the same. And they are also considering the projects from the interdisciplinary branches. So in this way, we can contribute to the Viksit Bharat Abhiyan, that is 2047. And other than Viksit Bharat Abhiyan, we can contribute to the ISRO basket, which is in my knowledge, because I am contributing one project in that one. So other than these 2 opportunities, you can also explore other opportunities at ANRF website. So that was initially Department of Science and Technology serve. So they have changed that one into Anusandhan now, ANRF. So you can explore that one also, Dr. Gaurav.
Okay, thank you, sir.
Thank you, Dr. Tesh, once again for this wonderful session. Thank you.
So there is one query from Obaid Ahmed Khan. If you allow, then I can give some suggestions.
Yes, sir, you can.
So here, sir is mentioning what are some potential projects that can be assigned to final year students related to 3D printing. Sir, for the same, what you can do, I have mentioned one case study on the second slide of this presentation. I'll be sharing this presentation with you. You can explore biomedical implant applications, where you can fabricate some biomedical implants using 3D printer.
Okay, sir, thank you.